I am presenting the following video on an article from the 2013 American Association of Physics Teachers, titled Obtaining Maxwell's Equations Heuristically. I'm going to fail miserably pronouncing the authors' names, but they are located at the bottom of the screen. The purpose of this article was to show the microscopic Maxwell equations for the electromagnetic fields can be deduced heuristically by using the transformation properties of the fields under their space inversion and time reversal. They used the experimental facts of charge conservation, electromagnetic waves propagate with the speed of light, and the Galilean invariance of the Lorentz force to finalize Maxwell's equations. They structured their article with the following 3 points: polar and actual vectors and time reversal properties, 2, the basic idea of generating the Maxwell equations, and 3, determining the constants in the choice of units. They start with classical mechanics and experimental evidence that the Lorentz force on a test particle with electronic charge q moving with a velocity given by the equation, the Lorentz force equals the q quantity of the electric field plus eta crossed with, times the velocity crossed with the magnetic field, where eta is a constant here. A particle with magnetic charges has never been observed, hence the fields are generated only by the electronic charges with charge density ρ and moving charges with current density J. Because of the multiplication connection between the charge and the fields, their units cannot be chosen for a particular reason. The transformational properties of vectors with respect to a spatial inversion are given from r to negative r. The vectors p that transform according to p prime equal negative p are called polar vectors, or just normal vectors. Vectors a that transform according to a prime equal a. These are called axial vectors. The following example shows the transformation properties of polar vectors, which are the position r vector and the momentum p vector, and the axial vector is the angular momentum vector, which is r cross p. This example, they explicitly depict the transformation properties of those polar and axial vectors. These following rules hold for multiplication of different types of vectors. That when you have one polar vector crossed with another polar vector, you get an axial vector. When you have two axial vectors crossed together, you get an axial vector. When you have one axial vector crossed with one polar vector, you get a polar vector. Just as there are polar and axial vectors, we can define following scalars under spatial inversion, where scalars s that transform according to s to s prime equaling s are just normal scalars. Scalars asterix that transform according to s asterix to s asterix prime equal negative s asterix are called axial scalars. And they can also be generated by the following properties. When you take the dot product of two polar vectors, they give you a scalar. When you take the dot product of two axial vectors, you get a scalar. And when you take that dot product of a polar vector and an axial vector, you get an axial scalar. We can now identify the vector and the scalar characters of the quantities together with their behavior under the reversal of time. Since the mass m is a scalar, the force times equals the mass times the acceleration is a polar vector with the force of negative t equals the force with respect to t. So therefore, because q here is a scalar from the first equation I wrote on the board for us, is a scale that q is a scalar. The electric field is a polar vector with the electric field with respect to r and negative t equals the electric field with respect to r and t. Because the velocity is a polar vector with the velocity of negative t equals the negative velocity with respect to t, due to the vector products, b, the electromagnetic field, is an actual vector with b of r with respect to negative t, giving us the negative magnetic field with respect to r and t. They dedicate the next section to the basic idea for generating the Maxwell equations. They do this by the dedication of the structure of the Maxwell equations from the principles of simplicity and linearity, with 5 undetermined constants. Only looking at 3 of the 5 for this moment in time. From the first one, we want to remember that there is no experimental evidence for magnetic charges, meaning there cannot exist any field-generating axial scalars. So the only axial scalar that can be generated and obeys linearity is that to take the first order spatial derivative of an actual field vector. So then we can conclude that the divergence of the magnetic field equals 0. So if the divergence were non-zero, then there would exist terms proportional to the angular momentum that would lead to an out-of-the-plane acceleration. And the electric field dotted with magnetic field violates the superposition principle. So for the second one, we can have the partial derivative of the magnetic field and the curl of the electric field, because remember from under time reversal that the axial vector crossed with a polar vector gives us a polar vector. So because a field-generating axial vector does not exist, the heuristic demand for simplicity and linearity leads us to the equation: the curl of the electric field plus chi multiplied by the partial derivative of the magnetic field equals 0, where chi here is the undetermined constant. For the third one, the only scalar that can be generated from the first derivatives of the fields without a sign change under time reversal is the divergence of the electric field, which this equals the scalar source term rho multiplied by alpha, where alpha is an undetermined constant. So finally, the only polar vectors that change sign under time reversal and that can be generated from the fields by the first order derivatives are the divergence of the electric field and the curl of the magnetic field. So these terms gives us the equation with current density. So the curl of the magnetic field plus the chi multiplied by the divergence of the electric field equals beta times the current density, where the constants chi and beta are still to be determined. These are still the 5 constants that we need to determine. This will lead me into the next section of the article. So we now need to determine the constants from what we just went over and how the basic idea of generating the Maxwell equations. And the first equation I provided for you, I will bring them back up further on through the talk so you aren't blanking from what I'm talking about. But to do this, we're going to determine it by using charge conservation, where the field generating quantities, rho and current density, must satisfy the continuing equation. The invariance of the Lorentz force. The Lorentz force must be invariant under a Galilean transformation, for the velocity is much less than the speed of light. And then the wave equation, where the universal propagation speed c, the speed of light, must be contained in the wave equation derivable from the equations obtained in the last section.